Hello and welcome. In this video, we'll be beginning the lecture set on ANOVA, or Analysis of Variance. We'll start out with a discussion in this video specifically on the relationship between ANOVA and experimental design, and then throughout the lecture set, we'll continue to some basic concepts, examples, and application. All right, well, let's get started. So again, our lecture today is going to be about ANOVA. We're going to start in our lecture videos with a discussion of experimental design, which if you aren't familiar with ANOVA, haven't seen it before, might sound a little weird, but we'll discuss the connection. It's something that you may not have seen, you may not see anywhere else, but that's one of the reasons I do like to talk about it. So it's a moderate fit to our content, but it's not perfect, and we'll talk about some of that too. Then we'll discuss kind of some background conceptual things regarding ANOVA before moving into a few examples of how an ANOVA is conducted. After that, we'll talk about something called post hoc comparisons, and we'll discuss what this means and when these are used. And then we'll discuss an extension of ANOVA that kind of opens a lot of doors called two-way ANOVA, where we introduce other relevant variables. And of course, after all this, we'll discuss how to implement all of it in R. So lots of fun things to look forward to here, or in software in general. So lots of fun things to look forward to here. And we'll jump into it. I know you're all so excited. All right, here we go. So experimental design. So bear with me for a bit. In study design, we kind of have two broad classifications, and don't get me wrong, there's a million ways to classify study designs. But for the sake of argument, we'll say that there's two. We can distinguish between experimental studies and observational studies. Now, experimental studies are studies where we have this ability to control what's going on in the study. In an observational study, I have no control. And essentially what that means is I just look at what happens. I observe, versus in an experiment where I manipulate. Specifically, the main distinction that we look for in experimental versus a non-experimental study is, do I have control over who is in what group? So for instance, I might look in a medical example at like a treatment group, a new drug, versus a control group, someone who got a placebo or didn't get anything at all. In a marketing case, maybe I look at someone who got my new marketing plan versus someone who got the standard marketing plan. And if I can control which clients go to which marketing campaigns, then in that case, we would call that an experiment because I have that level of control. So if you do have this, again, it's typically considered an experiment. If you don't have this, typically we say it's observational. Sometimes you'll hear something called quasi-experimental. There's a few different ways that we can define quasi-experimental, but one decent way is I can't control the groups of people, but I can control which group gets what. So like a classroom, I can't control, maybe I can't randomize students in classroom, but after the student groups are made, I can randomly select which classroom gets which teaching style or something like that. All right, so let's look at a couple examples. In a medical trial of a new drug, I can assign which patients get the new drug and which ones don't. So that's an experimental study. Another medical example, comparison of male and female blood pressure. This was a couple years ago. So it's been a minute since I've done this. I can't assign which patient has 2 X chromosomes versus 1 X chromosome. I can't switch that at the genetic level. And so in this case, this is an observational study. That's a characteristic that I can't modify, I can't control. I will mention that typically when we have control, we use random assignment to randomly select randomly assign which person goes into which group, or which group is assigned to which person. Also note quickly on this slide, and we might talk about this a bit later too, but on this slide you can see the experiment versus observational is not always a a question of, are you willing to put in the time, effort, money, whatever? In some cases, there's just not, it's just not possible to do an experimental study. And comparisons between males and females is a great example of, we just can't do an experimental study of that because we can't randomly assign people to one or the other of those two groups. All right, you may have heard in your previous stats courses or just elsewhere, correlation is not causation. And so this is worth mentioning again, and it's worth mentioning in this stats class. I feel like it's not a real stats class unless we say it. But correlation is not causation. So one of my favorite examples, there's a lot of examples like this, but one of my favorites that I tend to use is the relationship between ice cream sales and shark attacks in the United States. So those two are related. That's a fact. They are highly correlated. And the question is, well, what's going on? So if the fact that those are related implies that one causes the other, we have two directions that we can go. We can assume that ice cream causes shark attacks, or shark attacks causes ice cream sales. So shark attacks causes ice cream sales. Well, somebody gets eaten by a shark and then everybody wants to go buy ice cream. Yeah, no, that doesn't sound quite right. Or ice cream causes shark attacks. People eat ice cream and then sharks attack them to get their ice cream. Well, no, that doesn't sound quite right either. And what we're seeing here is an observational study design where I just observed that ice cream sales and shark attacks are related. I didn't control anything regarding that. And we're trying to make a causal claim from that. Now, what's really going on in this case, why there is a relationship, is because summer, it happens. And at summer, ice cream sales go up and shark attacks go up. And during the winter, ice cream sales go down and shark attacks go down. So there is an underlying explanation that said that to say there is a strong relationship between those things. It's just not a causal relationship. It's not because one causes the other one. It's because they are both outcomes of the same underlying thing. Now, in an experimental design, we eliminate some of that by randomly assigning individuals to different categories. Now, some of that isn't lost, but some of that is. And so random assignment in experimental design is necessary to do this causation. It's one of the necessary conditions. With observational studies, we just leave ourselves open to this type of thing. Now, I'll mention, even when you have an experimental design, you can still mess it up. Okay, so it's not that once you use an experimental design, now you get to make causal claims. So for instance, let's say I'm looking at marketing method A and marketing method B. And I kind of give out the marketing, let's say it's 2 flyers. I want to see which flyer is best. And I give out the regular flyer and I give it to somebody and I kind of frown, like, oh, here you go, here's a lame flyer. And then I give out my flyer to my group and I say, hey, here you go, isn't this the best product ever? And in that case, even if I randomly assign who I hand the flyer to, there's another thing going on there than just the marketing flyer. And so in that case, perhaps my attitude when I hand out the marketing flyer is as much or more important than the flyer itself. All that to say, even in that experimental design where I randomly assign people to group, I can still mess it up by doing things like that and a whole bunch of other stuff. So what we say is experiments are necessary, but not sufficient to establish causation. That is, I have to have it, but I also have to have some other things that make sense in order to establish causation. If I don't have an experiment, there are just some obvious flaws in the conclusions that I come to. Does that mean I can't come to any conclusions in an observational study? No, but there are some flaws associated with the logic. So I mentioned the benefits here of random assignment, and everybody likes to talk about causal connections, but sometimes random assignment isn't possible. We mentioned this earlier when we had the case of the number of X chromosomes. That's our second example here. But also we mentioned this earlier of like classrooms, students in a classroom. If I'm going to offer an educational program at schools, I can't really change the classrooms. They're already made. I have to go in and deal with what I have. And sometimes you have characteristics that can't be changed. So sometimes, again, it's just not possible. But in addition to not being possible, sometimes it's not ethical. So for a not ethical study, a classic example is smoking. Not ethical to take two people, randomly assign one to smoke 5 packs of cigarettes a day, and randomly assign the other to not smoke any cigarettes a day and just see what happens. But it's also the case that considering the study on ice cream and shark attacks, like consider what would have to happen for that to be an experimental design. Well, first I'd have to see which one I think causes what. So let's say I want to do an experimental design and I think people eating ice cream causes sharks to attack them. So to set up an experiment, and again, we wouldn't do this because it's not ethical, but think about what would be necessary to do an experiment there. I would take, say, 100 people out on a boat. I'd stuff half of them full of ice cream, and I'd toss all of them in the ocean. I'd see, do sharks eat the 50 ice cream people, or do sharks eat the 50 not ice cream people first? And if the proportion eaten in each group is the same, then I'd say, yeah, there's no evidence that ice cream is related or causes shark attacks. I'd have that experimental design. And maybe I'd smile at everybody as I throw them in the ocean so that there's no alternate factors. Again, I use this as a great example of something that's not ethical. It's just not ethical to conduct that type of study, and so we don't do that study. Another one, and I'll stop. This will be my last one, but it's another one of my favorites, is from the British Medical Journal. They publish a review of all of the randomized controlled trials of parachutes. And so in this review, they kind of talk about how there's never been any randomized controlled trials of parachutes. Well, how do we really know that they work? And the idea behind it is very tongue-in-cheek. The point being, in medicine, we don't always have randomized controlled trials. We don't always have experimental designs that have proven that medical practice or procedure is effective. And that's true. We don't always have that in medicine. But we don't necessarily require that a randomized controlled trial or an experimental design with a true control group be done to demonstrate the effectiveness. Rather, we just kind of stick with the standard of care, and then any new procedure we see, does it do better than what we currently have? Any new procedure or drug. And so the whole thing about the parachutes was, look, we don't have any randomized controlled trials or experimental designs of parachutes. And that's okay. Nobody's ever going to participate in an experimental control trial or a randomized control trial of parachutes, experimental trial of parachutes. I think the article ends, if I remember right, with the author saying something to the order of, for those who think that we need randomized controlled trials to know that something is effective, we encourage them to take part in the randomized controlled trial of parachutes. And again, very, very, very British. But in that case, again, it's just a case in point that while we do like experimental designs because they lead us to causal claims, we don't always get them. And that's okay. We kind of work with what we have. All right, so we've just talked a little bit about something that might seem completely random to you, experimental designs. So why do we talk about these in an ANOVA chapter? Well, first of all, it's good to know what ANOVA does, and then we'll talk about a little bit about why ANOVA and experimental designs go hand in hand. So ANOVA is just like a t-test. And in our ANOVA, we're essentially going to compare groups to one another. We're going to have multiple groups. So a t-test, I could compare two groups, say males and females, or airline A to airline U, I think was one of our examples. In an ANOVA, I can compare more than just two groups. I can compare airline A to airline U to airline D, and I can just keep going and make all of these different comparisons. So ANOVA is a powerful tool to compare two or more groups in a comparison. So that's what ANOVA does. That's all it is. It's essentially a t-test, but I want to compare more than just the two groups. Okay, so that's what ANOVA is. So why are we talking about experimental design in an ANOVA context? Well, if we're designing an experiment, we often, when we design an experiment, don't pick random things. We try things multiple times in the same place. What do I mean? Well, let's consider an example of baking cookies. So if I'm trying baking cookies, I'm going to bake a whole bunch of different sets of cookies. And I want to see what is the best cooking temperature. And I'm going to do an experiment to do that. Well, what I would do is I wouldn't try baking cookies at 257 degrees and 259 degrees and 225 degrees and 231 degrees. I would probably pick a couple of temperatures, maybe 325, 350, 375. And then based on those temperatures, I would put multiple cookies at that temperature and bake a bunch at those temperatures. I would pick a couple of standard temperatures that are somewhat wide apart, and I would bake the cookies, multiple sets of cookies at that. Why multiple sets? Well, because I want to make sure it wasn't just a one-off, wasn't just a bad cookie. I'd try multiple there and take the averages and compare between. Again, we're not doing these infinitesimally small comparisons, but what this means, temperature is a continuous variable. So what this means is even with a continuous variable, that's how we're basing our groups, we actually make a relatively small number of groups compared to what we could have. And ANOVA is a way in which we compare multiple groups. Again, t-test for just two groups, but ANOVA lets us compare as many groups as we want. So in my cookies example, right now I'd have three groups: the group at 325, the group at 350, and the group at 375. And I could compare all three of those using ANOVA. So in an experimental design, again, we tend to group our observations into groups. And that's why experimental design and ANOVA go hand in hand, is because so often we have these experimental designs that utilize the ANOVA analysis. But it's worth mentioning here, ANOVA is an analysis. It's a statistical analytic method. And experimental design is a study design. So these are two distinct things. Again, ANOVA, an analysis. Experimental design, a study design. Now that distinction, ANOVA being an analysis and experimental design being a study design, actually relates to our conversation about correlation and causation. Evidence for causation comes from the study design, not from the statistical method. Let me say that again. Evidence for causation comes from the study design and not from the statistical method. Remember, we said if it's an experiment, that's going to give us necessary but not sufficient strength to make a causal claim. But if it's an observation, it's not. Experiment and observations aren't statistical analysis. It's not ANOVA or t-test or correlation. It's not a statistical procedure. It's a methodological approach. It's a study design. So our evidence for the causation and a lot of the strength for causal claims comes not from the analysis, but from the study design. So what does this mean? What this means is all of the analyses that we have in class, so the ones we've already talked about, a Z and a t-test, or a test of proportions, or a test of variance, the ANOVA, things we haven't talked about but will, correlation, regression, all of these could give causal results. Yes, correlation can be causation, but what does it take? It takes a study design that is designed to yield causal claims. That includes an experiment, but that also includes other things, temporal precedence. That means the thing that caused the second thing came first in time. Temporal time precedence came before. So there's a few things that go into this to make a causal claim. Again, the analysis is not the deciding factor. It's the study design. This is kind of confusing because we say correlation is not causation. Again, correlation is a statistic. causation depends on the study design, and statistics and study designs are two separate things. So for me, a better phrasing is that correlation, it's not that correlation is never causal, it's that you can't assume correlation is causal. So maybe correlation is not always causation is a better way to look at it. Not correlation is never causation. Again, could correlation yield provide evidence for a causal claim? Yes, absolutely. If the study design is sound, if it's an experimental design, if there's temporal precedence, et cetera, et cetera, et cetera. But the determination from that is not whether or not you did a correlation. The determination from that is what was the design of the study. All right, so moving beyond, we're going to talk about some definitions, and then we'll jump into one other random thing real quick, and then we'll be done with this video and move on to actually doing our ANOVA. So factor. When I say the word factor, I mean a variable that's used in a study, and it's going to typically be categorical. This is in contrast to a level or a factor level, which is the values that the categorical variable could take on. So a good example here is think about eye color. Eye color is a factor, that's a categorical variable, and it could take on a whole bunch of different values: blue, green, brown, whatever, red. So in eye color is our variable. That's our factor, a categorical variable. And the levels are the different things that it could take on. Now, if you think about other categorical variables, participant sex, well, we would typically have male and female as the options for that. A participant's race, we might have black, white, Hispanic, etc., depending on who you ask. Hair color, well, we could do black, brown, red, blonde, purple, I don't know, we could do whatever. And again, you can kind of make up these lists. The factor levels don't necessarily have to be a closed list. The idea, though, is that the factor is a variable that can take on different categories, and the levels are simply the categories that that variable can take on. An experimental unit. So this is interesting. Often I do social research. And so for me, the numbers that I'm studying come from people. So I tend to talk about people a lot when I'm talking about these things. But it's worth mentioning and formally defining that we don't have to talk about people. Sometimes we're talking about cars or chairs or bolts or companies. We can talk about different units of analysis. The experimental unit is essentially the object of interest in the experiment. So what are we collecting the data from? And again, I use people often, but that's not always the case. Sometimes you'll see this shortened to EU. And if I'm trying to be formal, sometimes I'll drop in this term experimental unit or EU, but typically I just say people because, again, I do a lot of social research. All right, the last two are very important, and hopefully you've learned these in a previous course or have visited them in a review. If not, this is a good time to check these out. These are some good definitions, I think, but definitely check out, if this doesn't make sense, look up more on this. I think the best way to understand these next two terms are in the context of an experimental design where we're trying to find cause and effect. So for instance, let's say we're doing one of those unethical smoking studies, and I'm randomly putting people into smoking and not to see if smoking causes cancer. That's my goal. So this first concept, the independent variable, which is shortened to IV, and I'll use IV a lot, so that is a good shorthand to know. This is also called in different contexts a predictor, an exogenous variable, or an input variable. In the cause and effect study, the independent variable is the cause. So in the study to see if smoking causes cancer, the independent variable is whether you smoked or not. That would be our independent variable in that context. In the second variable, we have, it's called the dependent variable, shortens to DV, outcome, endogenous variable, output. I like output. But it's the idea of of what came out of the study. In a cause and effect variable, or in a cause and effect study, it is the effect that we're studying. So if I'm studying to see if smoking causes cancer, well, whether or not you got cancer would be the dependent variable. So the independent variable, did you smoke or not? The dependent variable, did you get cancer or not in the cause and effect study. So again, essentially what we're doing is we're changing in a cause and effect study, if we have experimental control, we're changing the independent variable and observing what happens in the dependent variable. And I said the word observe, that's okay. We have the control to change which group you went in, and we're seeing what is the outcome of that. What happens if I put you on a new blood pressure medicine? Does your blood pressure go down? What happens if I put you in a different course? Do you learn better? What happens if I give you a different manager with a different management style? Do you perform better, and do your colleagues find you to be more collegial? All of these things I can change potentially in an experimental design study, but even if I can't change them, I'm looking to see, did that thing have an effect? So in the management style, maybe I don't have cause and effect, but I see people who moved from one management style to the other, and then I want to see what came out of that. The management style is still the independent variable, and the dependent variable is level of collegiality or work productivity. And again, the goal is to assess how management style is related in that particular example to work productivity. All right, so that would be where we jump in, but I have one random note, and I apologize, but I just have to toss this in because we don't talk about this anywhere else, so you have to hear it from me. So, yeah, this is just completely random, completely out of the blue, and I just tossed it in here, so I apologize. All right, so this random note is talking about two different concepts, random assignment and random selection. So these are the two concepts that this is talking about. These sound very similar, but these are actually not similar to one another at all. These are not at all the same thing. Random selection has to do with how we pull people from the population into our sample. It has to do with how we pull people from the population into our sample. So random selection, if we randomly pull them, that is, we had access to everyone in the whole population, in the whole world, or in the whole world that we're considering. For the flights in airline A, I had access to all of the data for all of the days of all of the flights. And I randomly select the ones that I'm going to look at in this study. So I randomly select my sample from the population. That is random selection. What this does is this boosts the strength of my logical argument. And again, all stats is a logical argument, but this boosts the strength of my logical argument that my results from this group apply to everybody. Because again, this group was randomly pulled from everybody. There shouldn't be anything systematically different about this group than the whole population. So random selection has to do with how we select our group that we're going to study from all of the possible people we could have picked. And by doing that randomly, we feel more confident that any results that we find with this group of people apply to the larger group. That's random selection. Random assignment in this visual picture is after we have our group, how do we determine how we split them into, say, treatment and control? So after I've selected my people, this is after random selection, how do I determine how to split them when it comes to putting them in the different groups for the experiment? That is random assignment. So random assignment is, again, randomly assigning a person to one group or another. Now, what this does is this boosts the strength that the differences I find between groups is due to what I think it's due to. So let me give you an example. Let's say I'm trying to convince people that Dr. Florin's new curriculum is just the best ever. I mean, oh my gosh, it's just the best. And so if I'm trying to do this, I've got my group of people that agreed to participate in the study, and I've got somebody else's curriculum that I'm like, oh yeah, that curriculum's terrible. If, let's say we're a really unethical researcher, and I decided to go look at people's GPAs, and I'm going to give that person all the people with the worst GPAs, and I'm going to keep in my class all the people with the best GPAs in their previous math classes and stats classes. And at the end of the semester, all of my students have a better GPA, a better grade in my class than all of their students. Hey, my curriculum works better than everybody else's. I think that's the only answer there. Right? Maybe not. Well, in that case, I think you can clearly see that's problematic, right? Well, what went wrong? Well, in the group, when I chose how to assign the participants to the different groups, I biased that selection towards me. And so in that case, there's problems there. There's a lot of problems there that come up. And ultimately what that does is when I say the difference is due to my teaching being better, yeah, the classes are different. And then I kind of assume, well, that's because I taught differently. My new curriculum is the cause of the classes teaching better. If I didn't randomly assign, or if I did that unethical thing where I put everybody in my class, then the improved test scores in my course are not due to the curriculum being better. The improved test scores in my course are due to me stealing all the best students before the study even began. That's why the test scores in my curricular approach are better than everybody else's in that type of study design. Okay, I say all that to say random assignment prevents things like that from happening intentionally or accidentally. And actually, this stuff happens accidentally often, where kind of these correlations exist among people in different groups pre-existing, and that affects the outcome. So if I can randomly assign, I can prevent that from happening. And random assignment is a huge key in order to make confident claims that, well, if I randomly put the people in my group, randomly put the people in the other group, well, really then the only difference between these two groups is the different curriculum they got. So if my group does better at that case, maybe my curriculum is better. I feel a little bit more confident. There's not as many obvious flaws with that claim. So random assignment helps me feel more confident that when I see a group difference, it's for the reason I think it is. In this case, because the pedagogy is better, not for another reason. That is, not for the reason that the students just started at a better place. All right, well, we'll call that here for today. In this video, we talked about the beginnings of ANOVA and a lot about experimental design and some random things. Introduced a couple of terminology and notation that we're going to keep using through the rest of this course and the rest of this lecture set, of course. In any case, in the next videos, we'll be jumping right into more details on the actual analysis itself, now that we've gotten the experimental design concepts and some of the terminology out of the way. So thanks for sticking with me, and I'll look forward to catching you in the next video.